In section 2.5, we'll be going over the product and quotient rules. So we've already taken derivatives of sums and differences of two functions, and when we did that, we just simply added or subtracted their derivatives. But when we have products or quotients of two functions, we have to take the derivative a little differently. So first of all, it's important to note that the product of two differentiable functions, f and g, is itself differentiable. So if I know f and g are differentiable, if I multiply them, that function is also differentiable. But in order for us to take the derivative, we essentially just take the derivative of one piece at a time. And so when I take the derivative of f times g, it's f prime times g plus f times g prime. So notice I just take the derivative of one part at a time, multiply it by the regular other function. I could switch the order around because addition is commutative. That means the order doesn't matter. So you'll know you need to use product rule if you see two different functions being multiplied together. So for example, in number 1, we have h of x is 3x minus 2x squared times 5 plus 4x. So I see I have my first function, 3x minus 2x squared, and then my second part, 5 plus 4x. So those are my two functions. You can think of them as, those are your f of x and your g of x from that formula above. So when I find h prime of x, I'm going to take the derivative of the first part, so 3x minus 2x squared. That derivative is 3 minus 4x. Then I multiply it by the second part, 5 plus 4x. Notice I didn't take the derivative there, it's just the plain old second part. Plus in the middle, the first part, 3x minus 2x squared, times the derivative of the second part, which is 4. So this was my f prime times g plus f times g prime. Okay, so f prime g plus f g prime. Now on a free response question, I could leave my answer like this, but we're going to go ahead and work it out since we're doing it together. So I need to FOIL this piece, or expand it. 15 plus 12x minus 20x minus 16x squared plus 12x minus 8x squared. And then if I combine like terms, I'll get 15 plus 4x minus 24x squared. Now you might have asked yourself, did we really have to do all that? Did we have to use the product rule for example 1? And actually we didn't have to. We could have found it in a different way. And so we've actually done problems like that before. We could have expanded first. So if we expand h of x, just before we even took the derivative, just this function up here, we would have gotten 15x minus 2x squared minus 8x cubed. So really just FOILing there and combining like terms. And then I could just take the derivative using the power rule. So I'd have 15 minus 4x minus 24x squared. To me, that seems easier than using the product rule like we did up here. So it's your choice on a problem like this, but just know like if these get more complicated, like if you have like a trinomial times a trinomial, it might get a little messier and you might want to just use product rule, especially if you don't have to simplify. Like if I could just leave it right here, it's not too bad. But where product rule really comes in handy is when we're multiplying two different types of functions. So like a polynomial times an exponential or a trig or something like that. So let's take a look at some of those examples. So again, the first thing to notice is that you're multiplying two functions together. And so sometimes the multiplication symbol isn't clear. In part A, we have x sine of x. That's really x is my first function. Sine of x is my second function. So x times sine of x, those are my two parts. So when I take the derivative, I have the derivative of the first part, the derivative of x is 1, times the second part, sine x, plus x, times the derivative of sine x, which is cosine x. We can't really simplify this too much. You could just not have the 1 there. But otherwise, that's all we can do. That's our answer. Okay, part B, same idea. We have two different functions. We have e to the x, and we have x. So our derivative is the derivative of the first part, e to the x. Remember, the derivative of e to the x is itself, times the second part, x, plus the first part, e to the x, times the derivative of x, which is 1. You could leave your answer like that. If you want to simplify, usually what we would do is factor out that e to the x. So I'd have e to the x times x plus 1. It's probably how you'd see it on a multiple choice problem. Part C, we have h of x equals 2x cosine x minus 2 sine x. So you'll notice on this first term, I will have to use product rule. So I have 2x cosine x. And then this minus 2 sine x is just a totally different expression. I can just use my difference rule there. One thing that's going to help you is if you keep this 2 with the x. Think of that as its own special term. So that's like my f of x in this case. All right, so my derivative of 2x is 2 times the second part cosine x plus 2x times the derivative of cosine x, which is negative sine x. So that was just the derivative of this part. I had to use the product rule right here. Now I take the derivative of minus 2 sine x, which is minus 2 cosine x. And I will notice that my cosine x, the 2 cosine x, and the minus 2 cosine x cancel out. And so my answer is negative 2x sine x, just that middle term simplified. Last one, part D. I have x squared times natural log of x. So my first part is x squared. My second part is natural log of x. So k prime of x is the derivative of x squared, 2x, times natural log of x, plus my first part, x squared, times the derivative of natural log of x, which hopefully you remember is 1 over x. So we can simplify this a little bit. We've got 2x natural log of x plus, this is really x squared divided by x, so that would just leave me with an x. You could factor an x out in the front, but you don't have to. Now onto the quotient rule. So the quotient rule is a little bit easier to spot because it will be a rational function, so you'll see it as a fraction. So when we take the derivative of f over g, we get f prime times g minus f times g prime all over g squared. So you might notice that the numerator here looks a lot like the product rule, but there's one main difference, and that's the subtraction in the middle. When we have subtraction, we have to make sure that our order is that our terms are in the right order. So we have to make sure that f prime g is first and the f g prime is second. It didn't matter on product rule when we were adding, but it does matter with subtraction. And so we have a catchy little phrase to help you remember how to take this derivative, so what the quotient rule is. So you think of the numerator as the high function, the denominator as the low function. And when we say d, we're going to take that to mean the derivative. So the derivative of high over low is low d high minus high d low. You draw the line and square the low. Okay, so that's how we're going to remember the quotient rule. Okay, so let's go ahead and take our derivative. So we notice our two parts here. We have our high, 5x plus 2, our low, x squared minus 1. Again, we recognize we have to use the quotient rule. We see a quotient with multiple terms in the numerator and the denominator. So our derivative, dy dx, is low, so that's x squared minus 1. D high, so the derivative of the top, which is 5, minus high, 5x plus 2. D low, 2x, so derivative of the bottom, all over the bottom squared, low squared. Okay, so that was low, d high, minus high, d low, draw the line, square the low. Now again, on a free response question, I could leave it right here, but since we're working out together, we're going to go ahead and simplify it. One thing to keep in mind, I cannot cancel out this x squared minus 1. You will be tempted to probably, but remember I can only cancel something from the numerator and denominator if I can factor it out. There's no x squared minus 1 over here, so I can't actually cancel it. So when you're doing quotient rule, almost never can you actually cancel that out. We're going to go ahead and distribute. So we have 5x squared minus 5. And then over here, we're distributing as well. Be careful with this negative sign. Minus 10x squared minus 4x all over x squared minus 1 squared. Simplify a little bit more. Just combine like terms. 5x squared minus 10x squared would give me negative 5x squared minus 4x minus 5 all over x squared minus 1 squared. And that's my final answer. You don't need to worry about factoring the numerator or anything like that. In example 4, we're going to find the equation of the tangent line to y equals e to the x over 1 plus x squared at 1 comma e over 2. So remember, when we want to find the equation of a tangent line, whenever we see that, we automatically think about two things. We need a point, which is given to us, and we need the slope. In order to find the slope, we need the derivative, which is not given, so we'll need to find it. So when I take the derivative of e to the x over 1 plus x squared, I'm using quotient rule again. I recognize that this is a quotient, so I have to use quotient rule. So it's low, 1 plus x squared, d high, the derivative of e to the x is e to the x, minus high, e to the x, d low, the derivative of the bottom, 2x, all over 1 plus x squared squared. We can simplify this a little bit. In the numerator, we can factor out that e to the x, so we'll just make things look a little nicer. And we have x squared minus 2x plus 1 all over the quantity 1 plus x squared squared. Now remember, that's not my slope yet. I actually have to plug in x equals 1. The way I write that, I write dy dx and then an evaluation bar at x equals 1. And so I have e to the first times 1 squared minus 2 times 1 plus 1 all over 1 plus 1 squared. That gives me e times 0 over 4. But if I multiply anything by 0 and divide by a constant, that has to be 0. So if I have a 0 slope, that actually means this is a horizontal tangent. It didn't ask me about that, but it's just something to keep in mind. Now that I have my point and my slope, I can write my tangent line equation. So I have y minus my y coordinate, e over 2, equals my slope, 0, times x minus my x coordinate, 1. If you want to simplify that, this right side is going to completely cancel out because of that 0. And so we get that horizontal line, y equals e over 2. One important thing to note is that not every function that contains a quotient requires use of the quotient rule. Doesn't mean that you can't use the quotient rule, it just means that it might be overkill. So the way that you can tell that you don't have to use the quotient rule is if you have a single term in the denominator. This could also work if you just have a constant in the numerator, but we'll get more to that later. Okay, so here we have our function x squared plus 3x all divided by 6. That's just a constant. I can bring that out in the front. Remember that the derivative of a constant times a function is just the constant times the derivative of that function. So I can bring the 1 over 6 out in front. And so then when I take the derivative, that 1 over 6 just stays there. Then I multiply by the derivative of x squared plus 3x, which is 2x plus 3. And then I can simplify that, and I just have 2x plus 3 over 6. You could distribute if you want. You don't have to. So that's much easier than using the quotient rule. And again, I knew that because I just had a constant in the denominator. But that even works on something like b, where I have just a single term of x in the denominator. And so when I rewrite this, again, I'm going to rewrite the constant coefficients out in the front. And then I have my numerator. And you can think about dividing by x, or some people like to think of it as multiplied by x to the negative first. So then when I distribute that, 3x times x to the negative first would just be 3, or 3x over x. Minus 2x squared times x to the negative first would be minus 2x. So that's my simplified form of y. So when I take my derivative now, again, the constant can stay in the front, times the derivative of 3 minus 2x. The derivative of 3 is 0, derivative of minus 2x is minus 2. And so I just get 6 over 7 for my answer there. So again, this is much easier than doing the quotient rule. Although if you did the quotient rule, it would be okay, just probably too much work. It will be very common for you to see problems like example 6 on the AP exam. So what they're going to give you is a table of values of f and g and f prime and g prime. And they're going to ask you to find some derivatives of some functions that are made up of f and g. And so it's important in these cases, you want to find the derivative symbolically. So we don't actually know what f and g are, so we can't find the derivative functions, but we'll just think of their derivatives as f prime and g prime. So let's write the derivatives first, and then we'll go back up and look at the table to evaluate. So in part A, we're given h is equal to f of x over g of x, and we want to find h prime of 2. We recognize that it's the quotient, so I know I have to use quotient rule. So you always want to write your symbolic derivative first. So that means I'm just going to take the derivative of f over g. So it's my low, which is g of x, d high, f prime of x, minus high, f of x, d low, g prime of x, all over my low squared. Just writing that out for this function h of x is usually going to get you 1 point on the AP exam. The next thing we need to do, though, is find h prime of 2. So I'm just going to evaluate all of these at x equals 2. You don't necessarily need to write this part out, but it's going to help you keep track of your terms. Also, if you had other functions in there that had like actual x values, like square root of x or something, you would want to go ahead and plug it in. So now I'm going to look up at the table for my values at 2. So g of 2 was 3. F prime of 2 was negative 1. Minus f of 2, which is 4. And g prime of 2 is 3/2. All over, there was a g there. G of 2, which was 3 squared. Okay, so again, I just got those values from this table. Sorry, you can't actually see it in the video. So this was my f prime, g prime. Now, I can simplify that a little bit. I have negative 3 minus 6 all over 9, which is negative 9 over 9, which is negative 1. Again, on a free response problem, I could leave it right there, but you might want to simplify it. The last one, part B, I have the derivative of square root of x times f of x when x equals 4. And so remember, this is x to the 1/2 times f of x is really what we're thinking about. And so this would require the product rule. So that derivative is, when I do the product rule, I would have 1/2, derivative of the first part, 1/2 x to the negative 1/2 times f of x, plus the first part, square root of x, or x to the 1/2, times the derivative of the second part, which is just f prime of x. And then I'm going to evaluate that at x equals 4. That means I have 1 over 2 square root of 4 times f of 4 plus square root of 4 times f prime of 4. So 1 over 2 square root of 4 is just 1/4. F of 4 I can see from my table is 2, plus square root of 4 is 2, times f prime of 4 is negative 1. You do have to be careful and make sure you're looking at the right spot on your table. You have 1/2 minus 2, and that simplifies to negative 3 over 2. So again, remember, just take your derivative symbolically first, then evaluate, then use your table to plug in and simplify.